Hi, my name is Dailen Brown. I'm a research assistant working in the Precision Medical Instrument Design Lab at Penn State University. Today, I will introduce you to our work using simple computer vision methods to detect the usage of medical tools during simulated procedures. Through the use of haptics and other technologies, many simulation-based training systems for medical procedures have provided automated feedback and assessment on mechanical skills. However, there is a need for automated feedback and assessment of overall procedural correctness, which includes step order, sterile technique, and sharps management. These practices are typically assessed directly by experts. The use of experts during training is expensive, and their feedback can be subject to bias. The development of automated systems to replace expert oversight has the potential to improve training while reducing costs. Computer vision is one method which could be used to automate and standardize this evaluation process. Step order, sterile technique, and sharps management are difficult to assess using traditional sensing methods without inhibiting freedom of movement. Computer vision, on the other hand, only requires line of sight and can therefore remain out of the way of the user. Computer vision, paired with machine learning and artificial intelligence, is a powerful tool that has been used to classify diseases, automate image segmentation, and detect cancer. To investigate the validity of computer vision as an asset in procedural assessment, we developed and tested a simple algorithm to detect 6 medical tools commonly used in central venous catheterization, also known as CVC. The 6 tools used in this experiment are the syringe, the guide wire, the scalpel, the dilator, the sharps cup, and the catheter. Each tool was placed onto a tray with a monochromatic background. An algorithm was developed in MATLAB which first uses color thresholding to distinguish tools from the background, and then uses blob analysis to identify each detected tool. 2 experiments were performed. In the first experiment, the color of the background was changed to investigate the effects of background color on the algorithm's ability to distinguish between tools and the background itself. In the second experiment, the tools were placed onto a backlit tray, which was used to eliminate errors from shadowing. The algorithm was tested to evaluate its ability to detect and identify individual tools when placed alone on the tray and when placed all together on the tray. It should be noted that due to the small size of the screen, the catheter was not used in this experiment. The results from the first experiment indicated that white was the best color to use for the background. The measured percentage of the image which was detected as tools was plotted in this bar chart for each color. The estimated correct tool area, which was determined using a manual pixel count in Photoshop, was less than 7% and is indicated by the dashed red line. The white background was the only color to have a measured tool area that was lower than 7%. The green color was also close to the estimate, but by looking at the qualitative results, it becomes more clear. In these images, the black regions are pixels that were detected as being part of a tool, and the white pixels are detected as background. As you can see, the green background resulted in more error than the white background did. When placed individually on the backlit tray, the syringe, guide wire, and sharps cup were all detected 100% of the time, the dilator 90% of the time, and the scalpel 70% of the time. The system was in error most often when the scalpel was placed close to the tray's edge or when it was placed on its side. When all of the tools were placed together, the syringe, guide wire, and scalpel were each detected 100% of the time, the dilator 90% of the time, and the sharps cup 60% of the time. This is likely caused by the fact that the sharps cup has a lot of white on it, and when placed with other tools, it is often detected as part of an adjacent tool. Though the algorithm had some errors, it still shows the viability of computer vision as an asset in automated tool detection. The algorithm developed for this experiment is extremely simple, and with the use of more advanced methods, such as machine learning, the algorithm could become more accurate. Future work will be done to improve the algorithm, to develop methods to assess proper step order, sharps management, and sterile technique, and to integrate computer vision into current simulation systems. Thank you for viewing this presentation.